Hi to all. Today's topic, class 12 moving charge and magnetism chapter continuation I am going to explain. That is, today's topic is torque on current carrying loop in uniform magnetic field. That means if a current carrying loop is placed in the magnetic field, it will experiences the torque. That torque formula I am going to derive. Look at here, this is a current carrying loop. PQRS is a current carrying loop that is placed in the magnetic field, that means in between the north pole and south pole. The direction of the magnetic induction or the field is from north to south. The B is the magnetic induction, its direction is away from the north and towards south. Now I am placing this the current carrying loop in the magnetic field. Now in this moment what happens, right? On this loop torque will act, and due to the torque this will be rotates. On that torque, on what factors it will depends, that I am going to derive. I am going to derive the formula for that. By that we know that on what factors the torque depends. Torque means what? It is a rotating force. Okay. Previously we discussed when a current carrying wire, okay, whose length is L, if it is placed in the magnetic field of induction B, right? A current carrying wire of length L is placed in the magnetic field of induction B. Then it will experiences the force. The force formula is ILB sin theta. When a current carrying wire, if it is placed in the magnetic field, right, that current carrying wire experiences the force. That we know that force formula is ILB sin theta. I is the current in the wire, length of the wire is L, and B is the magnetic field, theta is the angle between the L and B. That already we know. And now let us see what are the terms that are present in this figure. Okay, look at here, PQRS are the rectangular current carrying loop, and I is the current in the loop, and B is the magnetic field applied by this north and south poles, and the next L is the length of the coil. Length of the coil is this one, and B is the breadth of the coil. Okay, and A is the area of rectangular loop. Area of rectangular loop formula is length into breadth, LB, area of rectangular loop. And theta is what? Okay, look at here, this one is the breadth, this one is the length, and this coil n cap is a unit vector. That direction is normal to the plane of coil. That means, for example, the rectangular coil is like this there, then the n cap will be like this there. For example, when the loop is like this there, okay, n cap is always perpendicular to the plane, right? And now it is just like area vector. Area vector is also perpendicular to the plane, perpendicular to the surface. Then here theta is angle between the normal drawn to the coil. Okay, normal drawn to the coil. For a coil you draw the normal perpendicular line, and then magnetic field. N cap is this one, red line is the n cap, and the blue line is the B, and the angle between the N and B is the theta. Theta is angle between the n cap and magnetic induction. Now let us see, when a rectangular current carrying loop is placed in the magnetic field, on each wire some force will act. Okay, look at here, on the PQ branch of wire some force will act, and what is its direction, and I want the force on PQ. Force on PQ arm. Okay, PQ arm. What is the force on PQ arm? That is F1. Let us consider. That force formula is what? Force formula is ILB sin theta. Okay, what is theta? Angle between the L and B. But here the theta is 90 degree because length is like this there, the field is like this there, right? Length and field. This hand is the field, length is like this there, the field is right side. That means like this, they are perpendicular to each other. Then we write ILB sin theta. Then what is the force on the PQ arm? That is ILB. Okay. Then force on RS arm I want to find out. Force on RS arm. Okay, right, what is that? We can take it as F2. Then that force formula is again ILB sine theta. Theta is again 90 because this arm length is also L because opposite sides are equal. Okay, and then we will get F2 also ILB. But what about the directions of these two forces? Okay, directions of these two forces, and not only these two sides, and more two sides are there, that is QR and PS. On that also forces will act, but on QR exactly upward force will act, on this PS exactly downward force. These two forces are equal and opposite, they will cancel with each other. And here, look at here, what about the force on this RS side? Force on RS side, we have to use the Fleming left hand rule. For that, you have to stretch the forefinger, central finger, thumb mutually perpendicular to each other. Forefinger indicates the magnetic field, central finger indicates the current, thumb indicates the magnetic force. Okay, this is the left hand rule we have to use to know the direction of the force on the loop, on the wire. And for that, to know the direction of the force on current carrying wire, we have to use the Fleming left hand rule. In the Fleming left hand rule, we have to stretch the forefinger, thumb, central finger of left hand in such a way that they are mutually perpendicular to each other. This forefinger indicates the magnetic field, central finger indicates the current, then the thumb indicates the force. Look at here, now you have to adjust the forefinger in the direction of the magnetic field, that is the right side. Central finger adjust in the downward, that is downward on the RS side, and thumb indicates the force is upward, the outward like this, right? Then this I will draw like this. This is indicates the force upward, that force is F2. And here the current direction is reversed, then the force direction also reverses, it will be downward, it will be like this there. That means now equal and opposite forces will act on the wire. For example, this is a rectangular loop. On this side the upward force will act, on this side downward force will act. It is fixed at the center. Then at that moment when equal and opposite forces makes to rotate this coil, okay, and that rotating force is called as torque. This equal and opposite forces F1 and F2 are equal and opposite. F1 and F2 are equal and opposite. Okay, they produce couple or torque. Okay, this equal and opposite forces are called as couple or torque on coil. Then what is the formula for the torque on coil? I want to derive the torque on coil. Torque on coil. Okay, in the torque formula we can derive, that formula is force into perpendicular distance between two forces. Perpendicular distance between two forces. This is the formula for the torque. Torque formula is force into perpendicular distance between two forces. Then how to derive the force? Already we know, that is F1 or F2 ILB. But perpendicular distance between the two forces we want. Force into, this is perpendicular symbol, perpendicular distance between, this is between B apostrophe, this one N, means between two forces. Force into perpendicular distance between two forces. This is the formula for torque. Then here I will draw the individually this diagram. Look at here, this is breadth, okay, this is length. I will draw this one. Okay, this is the breadth. Okay, this diagram. Here n cap means normal to the plane of the coil. Okay, right. And now n cap is a unit vector normal to the plane of coil, like this. If the coil is like this there, then if the coil is the book, now the n cap will be like this there, right? When the coil rotates, n cap also rotates. N cap is always perpendicular to the plane. And now force on this side, this I drawn it here. N cap will be like this there. N cap is this one. This is N cap, and this is the magnetic field. Okay, magnetic field is right side. Now this end, okay, this is the breadth. Okay, the breadth, this one. This angle is theta, we know already. Okay, B is right side, N cap, and this one small b. Small b is the breadth of the coil, capital B is the magnetic field. Okay, magnetic field right side. This branch I am drawing, this line, and the next N cap, and this AB, and angle between them is theta, right? What about the force on this side? The force on this side is upward, right? We know already, that is F2, and the force on this side is downward, that is F1. I want the perpendicular distance between the two forces. On this side force is upward, on this side force is downward, right, according to Fleming left hand rule. Now we have to know the perpendicular distance between the forces. We can form a rectangle here, a triangle here by using this. Right, and now this is R perpendicular distance between the two forces. Okay, R perpendicular. This is theta, means this line. Okay, N cap is perpendicular to this line. Look at here, N cap, this is the line, N cap is perpendicular to this line. Okay, this is the plane, and N cap is like this there, perpendicular will be there, perpendicular to surface. That means now this is theta. What about this one? Because this total angle is 90 degree, this part will become 90 minus theta. This is 90 minus theta, and this is 90, and then the sum of these three angles. Okay, then you will get like this. Here N cap, here field B, this angle is theta, and this angle is 90 minus theta, because sum of these two angles is 90. This is N cap. Okay, and now this is 90, and here angle we will get theta, because sum of three angles is 180 degree. Then according to that, here in the mathematics we will get angle at here is theta. Once again I will tell, don't be confused, it was very easy. First, this is B bar, this is N cap, this angle is theta, this N cap is perpendicular, this total angle is 190 degree, this is theta. Means what about this? This is 90 minus theta, this is 90 minus theta, and here you can do the extension, and this is 90 minus theta, 90, total 180 minus theta, but the sum of three angles in this triangle must be equal to 180. Then by that you will get the angle theta at here. Okay, right, and now here angle theta we got. R perpendicular I want to know, this R perpendicular distance between the two forces. Then for that, how to find out the perpendicular distance between the forces? The torque formula is F into R perpendicular. F into R perpendicular. Okay, right, and this is equation 1, 2. Let us consider this is 3. Okay, I want to know perpendicular distance. Okay, from figure, right? From figure we write sin theta. What do we write sin theta? Sin theta equal to opposite side. This is theta. This is theta. Sin theta equal to opposite side is R perpendicular by hypotenuse. Hypotenuse is this one. This is B. Hypotenuse is B. Hypotenuse is B. Then from this R perpendicular we will get as B sin theta. R perpendicular we will get as B sin theta. Now this R perpendicular we substitute in the equation 3, and a force is the perpendicular distance. Force is what? ILB. This is substitute. Then from equation 3, right, what you will get from equation 3? Okay, now you take the screenshot and note it. I am going to rub this diagram. Now from equation 3, what we write? From equation 3 we will get as from equation 3 torque formula is F into R perpendicular. But what is F? F is ILB. Is it right? F is the force, this one, equation 1. And R perpendicular we got as B sin theta. This one we can write like this, tau is equal to I into LB into B sin theta. But what is LB? LB is the length into breadth A, that is area of coil, right? Rectangular coil. Then we will get tau as IAB sin theta. Okay, right. This is the formula for the torque, and this is equation 4. And if a coil has only one turn, this is the formula. If the coil has n turns, if the coil has capital N turns, then torque tau is equal to NI AB sin theta. NIAB sin theta. Now this we can also write in vector form. How to write in vector form? Then for that we write that tau is equal to, in vector form, tau bar is equal, we write as Ni into AB sin theta, we write as A bar cross B bar. This is equation 6. Okay, what is A bar in this? Area vector. Okay, area vector. Its direction is always perpendicular to surface and its magnitude is equal to LV. And next we can also write the torque on a magnet. Okay, if a magnet is there, this NIA we can also write as magnetic moment. Okay, for example, this is a magnet. This magnet has a north pole, south pole. Okay, and this is the south pole and this is the north pole. This is the magnetic moment, and it is placed in the magnetic field, external magnetic field. It will experiences the torque. Then the torque on magnet we write as tau is equal to capital MB sin theta. Okay, MB sin theta. This is equation 6. Here capital M, when you compare the equation 5 and 6, 7, here M is the magnetic moment. Magnetic moment of bar magnet. In case of bar magnet we got the torque, this formula, but in case of coil formula, this one. Then coil also act as a bar magnet. Its magnetic moment we can write as magnetic moment of coil, we write as NIA. Okay, right. And now this is about torque and current carrying loop. Okay, now based on this, let us discuss on what factors the torque depends. Number of turns depends, current depends, area depends. Okay, magnetic field depends, angle between the area vector and field also depends. These are the terms on which the torque and current carrying loop depends. Okay, and let us go for one problem, and later I will close today's topic. Take the screenshot and note every point. Okay, let us discuss few cases in this. That is first case 1. When the torque will be maximum. Okay, if theta is 90 degree, then the torque will be maximum. If theta is 90 degree, right? Okay, and then torque become maximum because the torque formula is NIAB sin theta. NIAB sin theta. Theta is 90. Then we can get the maximum torque as NIAB. Now case 2, when the torque will become minimum. If angle is 0, if theta is 0, then torque become minimum. Then the tau is equal to NIAB sin theta formula. If you write theta as 0, NIAB sin 0 we will get. The sin 0 value is 0. Then the torque become minimum. Okay, let us go for one problem. Okay, look here, this is our question. A circular coil of 30 tons. Okay, circular coil of 30 tons. The number of solution, let us go for. Number of turns in the coil is 30. Circular coil, not rectangular. Radius they gives radius of the coil. Circular means radius will be there. Rectangle means length into breadth will be there. 8 centimeter radius. We can convert into meters. 8 into 10 to the power of minus 2 meters. Next, carrying a current. This circular current carrying coil carrying current 6 amperes. It is suspended vertically in uniform magnetic field of induction 1 Tesla. The magnetic field is 1 Tesla. Okay, and the field lines means field makes 60 degree with the normal. Theta is 60 degree. Question is that calculate the magnitude of torque that must be applied to prevent the coil from turning. Okay, look at here. This is a circular coil. It is placed in the magnetic field. Then on the circular coil, torque will act. It will rotate. But we want to stop the rotation. Then with how much torque it is trying to rotate. Then if you apply that much torque oppositely, then it cannot turn. The torque that you should apply to prevent the rotation is equal to the torque with which it is rotating. Right? The deflecting torque we have to find out. Then the torque is what? That is our question. Then the torque formula already we know. That is NIAB sin theta. Now substitute all values in this. N is what? 30. Number of turns 30. Into current is what? 6 amperes. Into area of coil. What is the area? A is the area of the coil. Coil is in circle shape. That's why pi r square. Pi r square. Pi is 3.14. Okay, we can write here area formula pi r square. Okay, pi is 3.14 into r square. Now substitute all the values in this. Area is equal to pi r square. Pi r square means here r value is what? Look at here, r value is 8 into 10 to the power of minus 2 whole square we write. Okay, here we substitute area. Area is 3.14 into, this one is 64 into 10 to the power of minus 4 into, what is this? NIA completed B sin theta. What is B at here? B is 1. Sin theta, sin 60. What is the value of sin 60? Okay, root 3 by 2. Sin 60 value is root 3 by 2. Now you can simplify this. We will get answer. Now I am going to rub and I am going to give one homework problem for you, and then with that we will close today's lecture. Okay, right. Now you can simplify this yourself, how much value you will get here. And now I am going to press the pause button, and then after that I will write the question for the homework. Okay, these are the two homework problems I am giving, and yourself you can try to solve these problems, and these are very easy. Look at here, a rectangular coil of sides 8 cm and 6 cm length breadth they gave, and they have the number of turns. This coil have 200 turns, number of turns they gave, carrying current 200 milliamperes. Milliamperes convert into ampere, 200 into 10 to the power of minus 3 ampere. Current, length, breadth they gave, and now this is placed in the magnetic field. The coil is placed in the magnetic field, that is 0.2 Tesla. That is along the x-axis. Field is along x-axis. The question is that what is the maximum torque? Maximum torque formula you know, that you can substitute. In which orientation does it experiences the maximum torque? How the coil should be there in order to experience the maximum torque? For which orientation of the coil is the torque 0? For which orientation the torque maximum? For which orientation torque is 0? And write the condition for stable and unstable equilibrium. Right, we know torque on electric dipole in uniform magnetic field. Here torque on coil in uniform magnetic field. This is a current carrying coil in the uniform magnetic field. Already torque on electric dipole we completed. Then in that we discussed about the stable and unstable equilibrium. The same conditions applied it here. Write the condition for the stable and unstable equilibrium of the coil. Okay, this is the first question. The next one more question is that a rectangular coil of 100 turns, the number of turns solution in this, for this I will write the given values for the second question. Number of turns is 100 and have the length 5 centimeters, 5 into 10 to the power of minus 2 meters, and the breadth is 4 centimeters, 4 into 10 to the power of minus 2 meters. Right, it is placed in the magnet, it is placed in when its plane parallel to a uniform magnetic field. Okay, the plane is parallel to the coil, plane is parallel to the uniform magnetic field. Then what is angle theta? Okay, and then the current they gave is, current in the diagram, in the question current they gave is 2 amperes. It experiences a torque, and the torque also they gave is 0.2 Newton meter. They are asking to find the magnitude of magnetic field. That means the question is B is what? In this one testing is that what is angle? How is the angle? Theta is angle. The torque formula we know already, that is NIAB sin theta. NIAB sin theta. Okay. In this the torque they gave, number of turns they gave, current they gave, area we can find out, length into breadth. Okay, B they gave, magnetic field we have to find out, B we have to find out, theta we have to know. Theta is what? Theta is angle between the normal to the plane of the coil and theta is angle between the normal to the plane of the coil and magnetic field. Here how magnetic field is there? Look at here. It is placed, its plane parallel to the magnetic field. That means this is the coil plane and field is like this there. Look at here. The field is parallel to the coil. Okay, then what is theta? Theta is not angle between the plane and magnetic field. Okay, look at here. This is the plane. Magnetic field is like this there. Plane, magnetic field, two are parallel to each other. In the question also they give plane parallel to magnetic field. Then what is the theta? Theta not 0. Theta is not angle between the plane and field. Theta is angle between the normal to the plane and field. Normal to the plane like this there. Field is like this there, because the field is parallel to the plane. Okay, field like this there, but the normal to the plane, how it will be there? It is like this there. That means now normal like this there, field like this there. Then here in this case theta is 90 degree. Theta is not angle between the plane and field. If you will say that the plane is like this there, the field also like this there, two are parallel, plane like this, field like this, then two are parallel, angle we cannot take 0, because in the torque formula NIAB sin theta, theta means it is angle between the normal to the plane of coil and magnetic field. Okay, normal to the plane of coil and magnetic field. One note point I will give. For example, note, if plane of coil makes alpha angle with magnetic field, then theta we take as 90 minus alpha. Okay, theta is 90 minus alpha. Okay, these are the solutions and you can try for it, and these two question solutions you can complete it and send the solutions to me and write the answer in the comment. Okay, thank you for watching my lectures. Till now, if you not subscribe my channel, subscribe channel, share to your friends.